Okay, in this video we're going to look at some transformations of trig functions. Specifically, we will be focusing on period change and phase shift. While not essential, understanding the other transformations that can happen to these functions is assumed. Trig functions can be transformed just like any other function, just like quadratics, parabolas, or square roots, or any other function. The main difference is that they are periodic, which means over time they repeat. Now, I see two examples here. We have a basic sine function, which sine and cosine are both waves that look something like this. And I can see its period if I look, for instance, from 0. I complete one cycle right here at 2 pi. So its period is 2 pi because that's the distance it takes to complete one full cycle. This graph over here, which might be looking ahead a bit, is the tangent. Tangent, again, I see these curves repeated over and over and over again. What's happening here is there are certain values that I cannot actually reach, and I have asymptotes, is what we will have. And my curve just goes up through those. And my period is actually shorter here. It will turn out that my period is going to be pi. More on that later. So we take these basic functions. We will also talk about the secant and cosecant. But we take these basic functions and we're going to put them through various transformations. So I see here a general sine function. I could also do this for cosine or tangent or secant, cosecant, cotangent. Any of those, basically the same things will apply. Now I will note on here, inside here you might see this written as b times x minus c in certain instances. Be aware, those don't mean exactly the same thing. There is a difference between the two of them. So when I have something like this, if there's a negative up front, then I know what that causes is a reflection in the x-axis. Now that's an up-down reflection. Things that are going up go down. Things that are up high move down low. This number a out in front is a vertical stretch or compression. For sine and cosine, this is something called the amplitude. Amplitude is a property of waves. It is the distance between this center value and the peak, the crest or trough down here at the bottom. So like this is my amplitude, this distance right in here. All right. Skipping over this for a moment, down here at the end I see plus d, which is just a straight vertical translation. You can think about this when you're calculating this. Whenever you put in some particular value for x, you'll get whatever value's out for the sine and multiply it. But then I just add or subtract some number at the end. So if I add or subtract, that will just move my y straight up and down. That's a vertical translation. Now let's look back to the inside. It may be written again as bx minus c or b times x minus c. These things will affect my x coordinates. B will give me a horizontal stretch or compression, and C will give me a horizontal translation. So my horizontal stretch or compression for anything periodic, this is going to lead to a period change. For a horizontal translation, well, for something periodic, we can say a horizontal translation has a special name, which is called a phase shift. The idea behind that name, it's mostly just kind of a fancy name for a horizontal translation, but the actual idea of it is if I translate this a little bit to the right or left, well, as I look from 0 to 2 pi, I'll still see one full period. I'll just be looking at a different piece of this. If I moved this, for example, a little bit over, I might be looking at this part of the graph instead, between my finger and my pen, which is still one full cycle, but not the normal piece of a graph that I would be looking at. So it's called a phase shift. So I'm going to show you how to find these two things, and then in a later video we will graph these and I will show you how to interpret them. So first off, we will focus on period change. Now for any trig function, again, up here I did a general sine. This would also apply to a cosine. A couple things that are a little bit different when I move to tangent, cotangent, secant, and cosecant. Well, really the big thing is we don't have amplitudes because we will no longer have waves. So for my period change, how I will calculate a period change is I'm going to take the natural, or sometimes called the fundamental period, and divide it by b. Whatever the coefficient of my x happens to be, whether it's factored out or whether it's multiplied in, I will divide by b. The natural period for sine, cosine, and secant and cosecant is 2 pi. For tangent and cotangent, it will turn out to just be pi. So that's the direct way of finding the period. So some examples I see down here. I see -3 times the sine of 6x. I look at these transformations. I can see there will be a reflection, so rather than my sine going up like it normally would, it will start by going down. I see an amplitude of 3, so this has been vertically stretched by 3. But my period, I will take the natural period of sine and divide by 6, which means my period will be pi over 3 when I simplify this. So that means when I graph this, if I look at any section of the graph that is pi over 3 long, I'm going to see everything that ever happens on this curve. That's the significance of the period. Let's look at something a little bit more complicated. If I come down here, g of x is equal to 5 minus the cosine of 2 times x plus pi over 4. Now you see here what's inside is written a little bit differently here. The 2 is factored out, but please be aware this is still all inside the cosine. This is what we would call the argument of the function. The argument of the cosine here is 2 times x plus pi over 4. I can see the other transformations that are happening here. If I look at the cosine, there's a negative, which means there is a reflection. This positive 5 over here is added, so that'll be a vertical translation. And this will be a phase shift, is what it's telling me about, although it might not be giving me the phase shift directly. Discuss that in a minute. But I pay attention to that too. If I wish to find the period, I will take that 2, and I will divide 2 pi by that 2. So this function right here is going to have a period of pi. One last example. You may see some things that are written as fractions, where like here I see x over 3. I could make this even more complicated if I had something like x over 2/3. But the general idea is, again, there's a vertical stretch. The amplitude of this function will be 2. This will change the period, and that minus pi is going to result in a phase shift. For the period, I will take 2 pi, and I will divide it by the coefficient of x. Now, x is over 3, which means the coefficient is actually 1/3. If I take 2 pi and I divide it by 1/3, that's the same as multiplying by the reciprocal, 2 pi times 3 over 1, or times 3. So I can see that my period would in fact be 6 pi. So that's a quick look at how to find the period when the period has been changed. If you ever see something where it's simply the argument of your sine, cosine, tangent, whatever, is just x and there's no 2 or 3 or possibly even a fraction or a pi or something strange. If it's just the cosine of x plus or minus a number, any of the other functions plus x plus or minus a number, that means there is no period change and you just have the natural period. All right. Now let's look at phase shift. So there is a direct method of finding phase shift. A phase shift is, in essence, a horizontal translation. So if I give you a trig function such as this, I'm going to take my argument and set it equal to 0. This is, in fact, how you found horizontal translations in the past. You may not have done this in this way specifically, but this is always why. For instance, you might recall if I had a problem like y equals x plus 5 squared minus 2, this 2 means 2 down. This plus 5 actually meant 5 to the left. And the reason is because of what we're about to do here. I'm going to take this argument, set it equal to 0, and solve. Solving will change the sign, which is why that was always opposite of how you expected it. So this is the direct method for finding a phase shift. So let's look at a couple examples. Right here I see 6x plus 3 pi over 4. So what I'm going to do is take this, set it equal to 0, and solve. I can subtract 3 pi over 4, and then I can divide by 6. Dividing by 6 is the same as multiplying by 1/6, which is ultimately the same as just sticking a factor of 6 into this denominator. So this will give me negative 3 pi over 24. I didn't really need to multiply that. This is negative pi over 8. So this means my phase shift is pi over 8 in the negative direction, so pi over 8 left. Let's take a look over here. So the argument of this function is all of this stuff. I got to include the 3 too. 3 times x minus pi over 6 is equal to 0. You're welcome to start by distributing, although truth be told, that's not really a necessary step. I could just as easily divide everything by 3 to start, which would give me that x minus pi over 6 is equal to 0, which means x is equal to pi over 6. Again, what does this tell me? It tells me that my phase shift is pi over 6 to the right in the positive direction. So this is a direct method of finding the phase shift, and it works pretty well. But there's this other method that I do want you to know that is very useful when it comes to graphing. And this is called the bookend method. The bookend method will change a little bit if you use a different function, but for sine and cosine you will always start by taking the argument and writing an inequality where that is between 0 and 2 pi. 0 less than or equal to bx minus c less than or equal to 2 pi. So I'm going to take that whole argument right there. For the first one right here I have 4x minus pi. So I would say 0 is less than or equal to 4x minus pi, which is less than or equal to 2 pi. Now I'm going to solve this. This is a 3-part inequality. I can add pi to all 3 parts of this inequality. 0 plus pi gives me pi. Adding pi here gets rid of it. Over here I get 3 pi. My next step in solving should be to divide by 4. If I divide by 4, I will get pi over 4. I will get x. And I will get 3 pi over 4. Now the reason this is useful, even though we can find the period directly, the period, for example, here is 2 pi over 4, or pi over 2. The usefulness of this is I have just found the phase shift, and what I have found down here is the phase shift plus 1 period. So if I wanted to find the period, or if I wanted to check my work, if I subtract 3 pi over 4 by pi over 4, that will give me 2 pi over 4, which is the period, pi over 2. That's how it's supposed to work. The other usefulness of this, and again, you'll see this in my next video, I'll show you some examples of graphing these things with phase shifts. These two numbers actually tell me where I will be graphing. So when I make this graph, my standard period, if I backtrack here for a minute, why did I go from 0 to 2 pi? Probably the question some of us have. Well, the reason I go from 0 to 2 pi is because when I'm graphing sine, cosine, really any of the functions, I'm thinking about quadrantal angles mainly. For sine and cosine, I need to go from 0 to 2 pi to complete a full circle. The sine of 0 we know is 0, the sine of pi over 2 is 1, the sine of pi is 0, the sine of 3 pi over 2 is negative 1, then I make a full circle and I'm back to 0. I set up this inequality in this way because I want to have the sine of 0 and the sine of pi over 2 and the sine of pi and 3 pi over 2 and 2 pi. Setting this up this way and then solving tells me what x needs to be, what x needs to go between to get those same values. The pi over 4 corresponds to a sine of 0. The 3 pi over 4, when I put this in for x, would correspond to a sine of 2 pi. That's the notion behind why I did this. I apologize, that was a bit of a backtrack. So when I do this, when I set this up, over here I'm solving when does 4x minus pi equal 0. Over here I'm solving when does 4x minus pi equal 2 pi. And in the process of doing this, I figure out my phase shift. I find another number that is my phase shift plus my period. So if I subtract the two of them, again, I can confirm that my period is 2 pi over 4, or pi over 2. So then, I have useful information when I go to graph this. And again, look for my next video when we do graph one of these. So I'm going to try the bookend method one more time. This time we'll use a cosine. For sine and cosine, we will use 0 to 2 pi. The argument of my cosine is x over 2 plus 2 pi over 3. I'm going to solve this, so I will subtract 2 pi over 3 from all three parts of this inequality. A little bit tricky. 2 pi is 6/3 of a pi. If I subtract 2/3, I'll be left with 4/3. Don't get confused here. I now need to multiply by 2 to get x by itself. If I multiply by 2, I will have negative 4 pi over 3. Multiplying by 2 is going to multiply it into the numerator. And over here, I will have 8 pi over 3. So this tells me right here, my phase shift is described by negative 4 pi over 3. So my phase shift, if I abbreviate, is 4 pi over 3 to the left. Right here, this is my period, this is my phase shift plus 1 period. So when I go to graph this, I will start from my phase shift. I'll have several points in the intermediate space, and then I will end my graph at 8 pi over 3. Again, that will make more sense when we see graphs. I do want you to focus on this method and learning this and understanding that what we get here, the phase shift is always described on the left-hand side for sine and cosine.